moving in an elevator. No doubt when you were traveling in an elevator upwards, you had that funny feeling in the bottom of your stomach that sensed like your stomach was being pulled down. Well, that's actually kind of what's happening, but instead of being pulled down, it's being left behind because the floor is moving your feet upwards. Now, when the floor moves your feet upwards, the floor not only counters the effect of gravity, but it also accelerates your body upwards, and that's why you feel heavier. So there are 7 scenarios that describe the feeling a passenger experiences when they move in an elevator. So the first scenario is when the elevator is stationary, so there's no acceleration. Here's the free body diagram of your body. There are 2 forces acting on it. There's the upward force, the normal force, and then there's the downward force of gravity acting on the object. Of course, we have the net force equal to 0, and the acceleration, well, you're not accelerating. So we can analyze this in terms of Newton's second law, which states that the net force is going to be equal to mass times acceleration, and we've said that we're not accelerating, we're stationary. So the 2 forces are normal force minus Fg. Normal force minus Fg is going to be equal to 0, which means that the normal force is going to be equal to your weight. So you just feel your weight. Now, the normal force is the force touching your body, giving you the sensation of the apparent weight that you feel. So normal force is the apparent weight acting on your body. Now, the second scenario, we're moving upward and we're speeding up. So that means that the motion, the force, and acceleration are all upwards, and that causes speeding up. So we say that it's a positive acceleration. Here's the free body diagram. 2 forces, still the normal force and gravity acting on your body. And the overall net force is positive, upward, which means that we have a positive acceleration. Now, force and net force and acceleration are always in the same direction, be it going up or going down. It's always in the same direction. So the net force is equal to mass times positive acceleration. So normal force minus Fg is equal to mass times the positive acceleration. So if we rearrange this, we see that the normal force is equal to your weight plus what's necessary to accelerate your body. So the normal force is going to be greater than your true weight, which means you're going to feel heavier. Now the next scenario, we're moving upward, but this time we're slowing down. That happens when we approach our final destination on the way up. So what do we have? We have the motion and the net force oppose one another. So we're slowing down. So if the motion is being opposed, that means the acceleration and force are downwards. So we have a normal force, the floor, pushing up. We have gravity pulling down. We're moving upward. Now this time we have a negative net force, and that's because we're slowing down. The net force overall is downward. Fg is more than the normal force. So let's show that. Newton's second law, F net is equal to m times negative a this time. And we have the normal force minus the weight is equal to mass times negative a. We rearrange this, and we see that the normal force is equal to your weight minus what it takes you to accelerate. You're slowing down, so it's actually easier. So the normal force is less than your weight, so you feel lighter. The fourth scenario, now we're going to be moving downward and we're going to speed up. So that's as if you're stepping into the elevator and you begin moving downward. And when you begin moving downward, well, we know that you're going to end up feeling lighter. So here are the 2 forces. The force of the floor, that's what you feel, right? The force of the floor, the F net, that's your apparent weight. And Fg, well, that's just your true weight. And we have the acceleration in a downward direction because the net force is in a downward direction. Set up Newton's second law. F net is equal to m times negative a. The 2 forces, normal minus the weight, is equal to mass times negative a. When we rearrange that, we see that the normal force is equal to the weight minus what's necessary to accelerate you. So that means that the normal force is less than your weight, so you feel lighter. So you feel lighter in this case because the surface is in a controlled fall. So you're standing on the floor surface, and that floor is held up by the elevator cable, and you're not in free fall. All it's doing is it's slowing the effect of gravity. So you're not going down at negative 9.8, you're going down less than negative 9.8. So you have some support there. It's not totally zero. So that means that your downward acceleration is going to end up being less than negative 9.81. And that's why we use elevators, because it's not very fun going from the 10th floor to 0 without an elevator. That's called free fall. So 5, we're moving downward, but this time we're slowing down. So we're going down in the elevator and we're reaching our final destination, so the elevator slows down. So what happens there? Well, we still have the two forces. For you to slow down, you have to have an upward net force, which means that the acceleration is in the upward direction. F net is equal to m times positive a. So we have Fn minus Fg is equal to m times positive a. And this works out to show us that the normal force now is greater than your weight. So you end up feeling heavier again. Normal force is your weight plus what's necessary to slow you down, an upward acceleration. So 6, we're moving at a constant speed this time. So this is actually kind of interesting. So this applies to any direction if you're going up or down. Same free body diagram, same analysis. You have an upward normal force and a downward force of gravity. There is no net force this time because there's no acceleration. Okay, net force and acceleration are both equal to 0. So when we set up our equation, F net is equal to n times 0, we see that the normal force is equal to our weight. So we feel normal. Everything's like as can be. The only thing we sense is we hear the elevator operating, but we can't actually tell what direction we're moving in because there's no normal, we don't have, our apparent weight is equal to our weight. So everything is as it should be. So when moving at a constant speed in a windowless elevator, so you have no visual cues, you can't tell if you're moving up or down because the normal force is equal to your weight. And this is the principle that amusement park ride designers use in many of their rides. So I recall going into a ride at Disney World where I walked into what was a fake elevator. And what they did at the beginning of the ride is they moved me up for about a foot. They did it slowly, but I did feel some upward motion because I felt heavier. And then they rocked the box, okay? And that gave me the sensation that, oh, I must be moving. I wasn't. It was just kind of rocking. But I was thinking I must be going upward because I was starting to go upward. And then what they did is they lowered the box. So I traveled 1 foot up and 1 foot down, and it gave me the sensation that I traveled in the upward direction for many seconds. I think it was about 10, 20 seconds, that part of the ride. So lastly, what happens if the cable breaks? What do you experience? Well, you experience what's called free fall or weightlessness, as if you weigh nothing because there's no floor supporting you. So the passenger and elevator fall at the same rate, negative 9.81. So the floor does not push up on the passenger. So that means the normal force is equal to 0. There is no normal force. You are on the surface, but you're not pushing on the surface. It means that the surface is not pushing with a normal force upward. So there's only that downward force acting on you. We have a negative F net. We have a negative acceleration. You're speeding up as you go down. So force net is equal to mass times negative A. We have a negative force, negative Fg, is equal to mass times negative A. And look what happens when you substitute Fg with mg. You see the masses cancel and the negatives cancel. which tells us then my downward acceleration is just g, negative 9.81 meters per second squared. So two things we learned from this is that an object falls at negative 9.81 meters per second squared, and there's a bonus thing that we just discovered, something that Galileo himself said, that mass does not affect the rate of fall. Okay, all objects fall at the same rate.